Hello everyone. Our group is going to present a research paper called Bright Heralded Single-Photon Source Saturating the Theoretical Single-Photon Purity. We are going to approach this in the order that is listed here. We're going to give first a brief motivation, then an introduction, then we are going to derive and explain various topics, and in the end we are going to show you the experimental realization and then the results and conclusion. So why is this work important? Well, single photon sources are a fundamental requirement in many quantum technologies. They enable secure communication, precise measurement, and scalable quantum computing. However, to be useful in real-world applications, these sources must be both pure and bright. High purity ensures that we emit one and only one photon at a time, reducing the chance of multi-photon events that can lead to errors. It also guarantees true quantum behavior like anti-bunching, which classical light cannot exhibit. On the other hand, high brightness means we can generate photons at a much higher rate. This is important for speeding up quantum operations and overcoming losses that naturally occur in optical systems. The challenge addressed in this paper is achieved high purity and high brightness simultaneously, which are often at odds with one another. The aim of this paper is to advance the performance of a heralded single-photon source by benchmarking and designing such a source with maximum purity and at the same time having high brightness. This addresses a gap in the field, since previously many experiments achieved high purity values, but it was never clear if those were at or near the fundamental limit, or if further improvement was possible. Furthermore, having a state-of-the-art experimental realization of a heralded source saturating this purity limit is a significant achievement because it indicates the source is essentially optimal in purity, and any remaining impurity is just because you want a certain brightness. How they achieve this is first by deriving the theoretical limit of purity, then by transforming this limit into terms of a measurable quantity called the coincidence to accidental ratio. And then in the end, they designed an experimental setup and implemented it, which actually reaches this theoretical limit in purity while having a high brightness as well. A heralded single photon source uses a nonlinear medium to split an input photon, here called the pump photon, into an entangled photon pair. These two photons are then immediately separated into different paths via optical filtering, and this enables to herald, which here means to indicate the existence of one photon by detecting the other. Typically, the photon in the heralding arm, the upper one here, is called the signal photon, and the one in the heralded arm is called the idler photon. And such a photon pair can be produced by two processes mainly. One is called spontaneous parametric down conversion, and the other one is spontaneous four-wave mixing. In this research paper, they have used spontaneous four-wave mixing, so we'll go into more detail of this process later. What is single photon purity? As mentioned before, single photon purity refers to how close the output state is to a single photon number state. In other words, this means in a perfectly pure single photon source, you always get one output photon and never two or more. For the heralded case, purity is quantified by the heralded second order autocorrelation function at zero delay. And this basically tells us that given a successful detection in the heralding arm, what is the probability of having exactly one photon versus accidentally having two or more in the heralded arm? That's basically what the heralded second order autocorrelation function at zero delay says. Furthermore, if you have this autocorrelation function at zero, means that there is zero probability of having two photons in the heralded arm. Whether this limit can be achieved, though, will be derived later. And what is the coincidence to accidental ratio? Again, to recapitulate quickly, that's the quantity that the fundamental limit will be transformed in order to being able to measure it. And the coincidence to accidental ratio is a metric used to characterize the quality and performance of photon pair sources. And it is defined by the coincidence count divided by accidental counts. In our case, a coincident count means both detectors click simultaneously within a certain time window. This indicates that the pair was produced. To measure this quantity, you simply count how many times both detectors click together within this time window. However, an accidental count is when the detector clicks within the timing window, but not due to the same pair of photons. You can measure this quantity by shifting one detector's timing window by a delay much greater than the photon correlation time. And because no neutrino photon pairs survive such large delays, any clicks that you measure are due purely accidental photon pairs, which means the second photon could be due to the background radiation. Therefore, CAR essentially measures the signal-to-noise ratio of the pair source. A high CAR means that almost all clicks are due to true pair events with very few coincidences. In the paper, CAR is used to measure the theoretical limit of the Heralded second-order autocorrelation function at zero delay. In spontaneous four-wave mixing, two pump photons scatter through the third-order nonlinearity of the material to generate a signal and idler photon. So in this case, actually we have two input photons and two output photons. The output photons are entangled because of energy conservation. So which means if we measure the frequency of one photon, we immediately know the frequency of the other one without measuring it. Furthermore, in this part, we are going to derive the interaction Hamiltonian of this process. And the interaction Hamiltonian describes how the fields interact, such as photon pair generation via nonlinear effects. The derivation starts in reference 4 of the research paper, and they start by writing down the coupled classical wave equations that describe the evolution of the pump signal and idler fields in a nonlinear medium. These equations serve as the starting point for our quantization. So in the next step, we are going to quantize those fields. To move from the classical model to the quantum model, we apply the quantum correspondence principle, which allows us to replace the classical fields with quantum field operators. These operators can be seen down here, and as you can see, they contain the ladder operators. The quantum correspondence principle here pretty much states that quantum systems must reduce to classical physics in the appropriate limit. And in practice, it's often used to translate classical field expressions into quantum operator form. The final expression of the interaction Hamiltonian is then constructed in such a way so that it leads to the equations of the previous slide via the Heisenberg equation of motion for the field operators, which can be seen here. This results in this form of the interaction Hamiltonian. So, next we're going to look at the output state of spontaneous four-wave mixing. And we're going to do that by using first-order perturbation theory on the interaction Hamiltonian that we have seen on the previous slide. And the result for the first result for the output state looks like this. And as you can see, you multiply it by the vacuum state. And since we have seen that the quantum field operators are in terms of the ladder operators, some of the terms in interaction Hamiltonian are going to be annihilated. And then we end up with the 4-photon scattering term of the Hamiltonian, which is this part. And if we perform the first order perturbation theory on the 4-photon scattered Hamiltonian term, then we end up with the expression on this slide, which is the final expression of our output state. And as you can see, the output state is a superposition of the vacuum state and the 2-photon state containing the signal and idler photon. And this function here is the joint spectral amplitude, and it basically encodes the probability amplitude of generating the 2-photon states.
Okay, so Lars has given us already a brief overview about the paper, and it explains spontaneous four-way mixing process and its output states in detail. So building upon that, I'll be explaining heralding and achieving the theoretical limit of purity for single photon sources in detail. Okay, so let us start with heralding. So whenever we pump a non-linear medium of second order susceptibility or third order susceptibility with a pump of certain frequencies, we get probabilistic simultaneous generation of photon pairs. So if we'll detect a photon in heralding arm, there's a 100% certainty that there will be another photon with some frequency. So we can utilize this photon for quantum applications in metrology and sensing, and several other possibilities are there. But we want an output like this, a pure single photon source, and we are getting what we are getting in case of spontaneous Fourier mixing is a multi-mode spectrum of frequencies. So basically what I mean here is by multi-mode spectrum is the output that we are getting here in spontaneous Fourier mixing, the states are entangled. So if we'll measure one photon in heralding arm, it will project the heralded photon into some mixed state, which is no use for us because it's not of very good purity. So what should we do about it? Okay, so regarding the entangled state that you are getting from spontaneous Fourier mixing process, what should we do about it? Because we are not able to achieve what we wanted to. So what we can do is, one of the solution is optical filtering. Put optical filters in front of the output, whatever output that we were getting. So like it has been shown in this figure, this was the output that we were getting. We are applying optical filtering, which has been shown by this delta function. So we are only choosing a bandwidth of frequencies to allow through these filters. And what this do is, this makes our output states to look like a product state. So if now we will do a measurement on signal photon, it won't project this photon into the mixed state. So we are close to achieving a single photon of great purity. But okay, applying optical filtering definitely helped us to reach purity close to 1, but it costed us the brightness and the heralding efficiency, which are one of the drawbacks of the optical filtering process, which we'll see in which has been like shown in this experiment, like for what brightness, how much purity that we can achieve. But from here what we can conclude is, single mode emission is a fundamental requirement for unit purity. We want photon generated through this process to be in product state, so we can go as close to as purity 1. Since now we have looked upon the concept of single photon purity, we know what our aim is, but how to quantify the purity of single photon is, we'll quantify the single photon purity using second order correlation function. So what a second order correlation function is? Second order correlation function gives us the intensity correlation at detector D4 and a detector D3. So in second order correlation function, we are studying how is the probability of detection here is affecting the probability of detection to another detector. So let us understand it in detail. Suppose we have a laser, a coherent source at port 1, and at port 2 we have nothing. Like by nothing I mean vacuum. So what we will see here at detector D3 and D4, we'll get random coincidences, because in case of laser or coherent source, photons are coming independently and randomly. So they are in such no correlation except by random chance. So for that case, we'll always get a correlation function equals to 1, which I will show in next slide. But let us see another case. For a thermal source, which is also a classical source, for a thermal source generates photons in bunches. So what this beam splitter would do is, the beam splitter would divide the incoming bunch into the 50-50%. So 50% of the photon will go to D3 and 50% of the photon will go to D4. So whenever we'll see coincidences at D3 and D4, whenever there will be a bright spot, there will also be a bright spot, and when there are no photons, there will be no photons here and no photons here. So they are correlated in the sense that the probability of coincidence is twice as likely that we were getting in case of a coherent source. But if we insert some time delay in one of the arms of this detector, what we will see, the thermal source also will approach to the correlations as that we saw in case of a coherent source. Now let us talk about the single photon source. Since there is only a single photon coming at the port 1, so it could either go to detector D3 or it could either go to detector D4. It can't be at the both places at the same time. So in that case, we'll get a correlation function 0, which I will show you in the next slide. So, but what is the important thing here? This was the phenomena G20 equals to 0. It was not explained classically. There is no classical analog of it. And this was a very surprising result that Henbury, Brown, and Twist got through this interferometer setup, which we'll use to quantify our single photon purity. So from here, what we can conclude is for single photon, G20 is 0. Okay, so since we have discussed about different sources behave in an HBT setup, let us look at the distribution that they follow as well. So for a coherent source, since the photons are random and independent as well, so they follows a Poissonian distribution. Thermal source will follow a super-Poissonian distribution, like we can see from here. This speak that the chances of coincidence are twice as likely in case of a coherent source at 0 time delay. But the important thing here is this the sub-Poissonian distribution. For a single photon source, we were getting a dip which was not like seen classically and has no classical explanation to it. And this sub-Poissonian distribution is of great importance and great interest to us that we are using to quantify the purity of single photon source. So if we write the G20 function in case of Fock state, this comes out to be this. And now from here we are sure that for single photon source, G20 is 0, and that is what we are trying to achieve in this paper. Okay, so now we will look at heralded autocorrelation function at 0 delay. It's totally what we looked into earlier. It's just that it is a conditioned second order correlation function. Conditioned in the sense that firstly, we are detecting a photon in one of the heralding arm, and then we are measuring the correlation over the heralded arm for signal photon. So we are here calculating the correlation based on the post measurement state that we get here, and what we see is this correlation function is dependent upon the average number of photon per pulse that we get here. Now we will see how we will reach this heralded autocorrelation function in the next slide. Okay, so all the measurements that we're making in heralding and heralded arm are completely independent of each other. So we can replace them with their number operators. And now for a general probability distribution, and we were getting simultaneous photon pair generation in this process, we can write the output state to be like this. And then by putting and calculating the average of the state, we get G2 H0 to be dependent upon this mu, which is the average number of photon per pulse you are getting, which is experimentally very hard to calculate. So we have solved one problem using optical filtering, and now we are stuck at another. Now what should we do about it? So in the next slide, we'll look into the solution of this one. Okay, since mu was very hard to measure experimentally, we need to look into other ways to get better theoretical purity relation. So for that, CAR comes to be our savior. CAR is basically coincidence to accidental photon detection ratio. And this is a similar setup like HBT setup. What we study here is CAR is given by coincidence counts divided by accidental counts. Coincidences count maybe occur because of the actual photon pair generation, or it might be because of the noisy counts. So we need to differentiate among those counts. That are we doing using this concept of matched slots and unmatched slots, and we are calculating the accidental counts which are given by the unmatched slots. Here we are subtracting the coincident counts because of the pure photon pairs that we actually aimed, and here are the accidental counts, and using that we can calculate CAR, and which we'll see further what this CAR gives to us. Okay, so as explained by Lars, the output state and spontaneous Fourier mixing process follow Poisson distribution, and their detection efficiency, the probability of detection, is given by this expression where alpha is the collection efficiency of the channel. So we calculate R true is the true coincidence photon count rate, and R accidental, and from these two terms we calculate that CAR is dependent upon the average photon pulse rates. So now we know the link. G2H0 was also dependent upon the mu, and CAR is also dependent on mu, and CAR is easily measurable experimentally. So, okay, so like I was saying in the previous slide, that CAR and G2H0 has a common link mu, which are the average number of photon per pulse that we are getting. Since mu is experimentally hard to measure and CAR and G2H0 common link, using these two equations we can get a equation between G2H0 and CAR, and since CAR is very easy to measure experimentally, we can find out what our G2H0 would look like, and this would give us the theoretical limit of the purity, which has been shown in this figure. This is the maximum limit with coherent pump that we can reach using this CAR method that has been experimentally realized in this paper, which will be discussed in detail by Tanya and Garima.
Hello, I am Garima, and I am here to explain the experimental setup of my experiment, which is shown here as well. And this diagram is from the paper only. Now, first of all, I'll explain the flowchart of the process. Uh, so in the flow chart, we have a continuous wave master laser. Then this master laser is acting as a seed laser to a slave laser, which is on gain switched uh, mode. And then we are using an amplifier to amplify our signal even more. But this amplifier is producing some ASC noise as well. Then after this, we are filtering our output after the amplification using two optical filters, which is fiber Bragg grating and further by band pass filter. Then our 10% of the output is sent to the PM, which is monitoring if the intensity fluctuation is more or less, or power fluctuation is more or less, and then it is acting as a feedback mechanism to OA and sending its measurements to VOA, which then acts which is a variable optical power meter, which then just the output. If it is if the power is less, then it will be uh, if the power is less or more, it will adjust accordingly and will give the desired result. And after that, we are using polarization controller, which aligns the pump to TE mode, which is essential for SFWM in spiral waveguide. Also here we are using this HBT schematic one, which I'll explain how is it working. Now let's see the detailed explanation of all the apparatus which we are using here. So let's get started. So first of all, we'll see we need the theoretical limit attained above, which is explained by Diksha, can be demonstrated with an experimental setup. So, which the experimental setup in which the conditions in which these conditions are taken care of. So, first of all, stable high purity pulses should be there for efficient photon generation. Then reduce noise and time jitter, improving heralded single photon purity. Then spectrally clean pulses, which we need, minimizing excess background noise as well. Now, the ML, which is master laser, I have talked about first of all in the diagram as well. The master laser operates in continuous wave mode, emitting a stable optical signal at 1550.52 nanometer. The master slave provides a clean frequency reference to control and stabilize the slave laser through optical injection locking. So basically, as I have made a table as well, master laser is acting as a seed laser to slave laser. So slave laser is binded to have the frequency of the master laser. Now, slave laser is a semiconductor distributed feedback laser that generates 2.5 gigahertz, 70 picosecond optical pulses at the frequency of the master laser only. It operates using a technique called gain switching. Now, what is gain switching is where the laser is driven with a high frequency electrical modulation to force it into short pulse generation. If the now we are using gain switching because if the SL were left to operate freely, it could exhibit significant time jitter and frequency instability, and that's where injection locking is useful. Now, how SL is operating? The SL is initially below its lasing threshold. So basically, I'm explaining here gain switching. The SL is initially below its threshold limit, meaning it does not emit light. Then a high frequency electrical current is applied to the SL. This modulation quickly pushes the laser above and below threshold, causing a rapid burst of optical emission. Hence, the result which we get is a short optical pulse instead of continuous beam. Now, without this procedure, we would not be able to get the high stable output which we are getting here. And now I'll explain about optical injection locking. So basically, this technique where a high power laser, a slave laser is stabilized using a low noise master laser. And this is what optical injection locking is. And this ensures that the slave laser operates at exactly the frequency of the injected master laser. As I have already told you that a slave laser is forced to work upon the frequency of the master laser. Uh, Basically, I have written the key benefits here as well. Ensures frequency, stability, and coherence. Produces short, stable pulses with low jitter. Reduces noise and optical. Improves purity. Now, after that, as we have seen here, that after the slave laser, we have the amplifier, which is EDFA. So the optical pulse generated from SL has relatively low power. So they are amplified using an EDFA. EDFA is erbium doped fiber amplifier. So EDFA is boosts the signal power without converting it into an electrical signal. It consists of erbium doped optical fiber pumped by 980 nanometer or 1480 nanometer laser diodes. Now, EDFA is used because there is no noise amplification using EDFA and a high gain. And yes, but EDFA introduces a problem here as well. It introduces noise here. Because EDFA introduces amplified spontaneous emission noise, ASE, as I've told you, which consists of unwanted photons across a broad spectrum and background noise that degrades single photon purity, which we do not want here for our experiment. So to tackling this problem, we have optical filtering, and we have two optical filters we are using here, which is FBG and BPF. So optical filtering is a crucial step as we can see because of the noise introduced by EDFA, and a crucial step in ensuring that only the desired wavelength are utilized while eliminating unwanted broadband noise. So fiber optical grating is used first, which is an optical component consisting of a periodic variation in the refractive index along the length of an optical fiber. So here, role of FBG in the setup is that it is used here as a full width at half maxima of 0.4 nanometer, meaning it allows only a very narrow range of wavelengths to pass through. It effectively filters out unwanted broadband amplified spontaneous emission, ASC noise, which was introduced with the pump pulses. The desired pump wavelength is selectively retained while all the other, let's say, unwanted wavelengths are blocked. This step is essential for ensuring clean and stable pump. And following the FBG, a tunable band pass filter is used for to further refine the spectral purity of the pump light. So role of VPS in the setup is so the BPS here, which we are using, has a narrow passband of 0.3 nanometer, meaning it allows an even more precise selection of the pump wavelength as compared to FBG. So we are ensuring even more filtering here. It rejecting any remaining noise. It provides additional filtering to remove any residual ASC noise that might have passed through the FBG. Since our BPF is tunable, it allows for fine adjustments in the filtered wavelengths, offering flexibility in selecting the exact pump frequency required for the experiment. Using not all, using both these filters, the filtering performance is enhanced. The system achieves here an optical isolation greater. So the reason is the VOA dynamically adjusts the power of the pump beam to maintain a stable intensity. If the PM continuously measuring the output power after the VOA has adjusted the intensity, if the PM were placed before the VOA, it would only detect fluctuations, but not the final adjusted power. And hence, it is placed after VOA. Now, our Okay, let's talk about HBT as well. Here, HBT is in this experimental setup, the Hanbury, Brown, and Twist setup, which is shown here at position 1, is used to characterize the intensity fluctuation of the pump laser before it enters the spiral waveguide. It is needed because it measures the second order correlation function of the pump. This helps determine whether the pump exhibit intensity, noise, or fluctuations. How it works? The HBT interferometer consists of 50-50 beam splitter and two single photon detectors. It records the time difference between detected photons and builds a correlation function. If the pump is ideal, then our according to the Poisson statistics, second order correlation function is 1. And if there is any intensity fluctuation, then it would be greater than 1, which would indicate an incoherent pump. Now, key purpose of HBT is it verifies that it verifies the coherence and stability of the pump before non-linear interaction, and it helps quantify the impact of intensity fluctuations on the single photon purity of the heralded source. And now our output pulse is ready to go into the spiral waveguide, which will be explained by Tanya. Thank you. The system achieves an optical isolation of 106 decibel, meaning that the noise photons are suppressed by a factor of 10 raised to power 10, which is huge here. Then we are using active pump power stabilization. Even after optical filtering, stabilizing the pump power is essential to maintain the reliability of the SFWM process. Any fluctuation in pump power can have a direct impact on the system's performance, which we do not want here. So key components of power stabilization we are using here is optical power meter with 10:90 tab beam splitter. So 90 tab beam splitter is introduced after the optical filtering stage. 10% of the pump power is directed toward an optical power meter, which continuously measures the power level. And 90% of the pump power continues towards the waveguide, where it is used for SFWM. Then the PM provides real-time feedback on power fluctuations, uh, which is directed towards the variable optical attenuator. Once the power meter detects fluctuations, VOA is used to actively regulate the pump power. The VOA dynamically adjusts the intensity of the pump beam based on feedback from the power meter. If PM detects excess power, the VOA reduces the intensity to prevent fluctuations that could affect photon pair generation. If the PM detects a drop in power, the VOA allows more light through, compensating for the loss. So this feedback loop ensures that the pump power remains at a constant, stable level. Then we have polarization control for efficient SFWM. Why is polarization important? Before the pump enters the silicon spiral waveguide, it is necessary to align its polarization to the waveguide's mode. Silicon spiral waveguide supports only TE mode, which Tanya will explain more in detail. If the pump light has random polarization, only a fraction of it couples efficiently into the waveguide. This leads to inefficient SFWM and reduced photon pair generation. And polarization control is doing exactly what we want here, which is placed before the waveguide input. The PC adjusts the pump polarization so that all of the pump power is in the TE mode. This ensures maximum non-linear interaction in the SFWM process. Now, why is PM placed after the VOA? As we see here, that PM is placed after VOA. So, as Garima already explained the experimental setup for the for this paper, so I am going to explain the spiral waveguide. So, why we are using the spiral waveguide? What are the purpose? What are the benefit for specifying using the spiral waveguide? spiral waveguide. Why we are using the silicon waveguide? This is the spiral structure of the waveguide. So yeah, so purpose of the spiral waveguide is like we have a pump photon and we want to convert pump photon into two photon, which is signal photon and idler photon. So pump photon frequency is omega p and wavelength is 150.52 nanometer into signal photon omega is 1546.92 nanometer and idler photon omega is 1554.94 nanometer. Symmetrically spaced frequency. So this my signal photon and idler photon is like symmetrically spaced frequency around the pump photon. So that's why my omega is omega p plus delta omega and omega I is omega p minus delta omega. So my delta omega is 1.8 terahertz. So why all these conditions are because of the energy conservation. So my energy conservation is 2 h cut. So like my initial energy of the pump photon, which is equal to my signal photon and idler photon. So this is the relation. So total pump energy is divided into the signal and idler photon energy. So this is the purpose that we are want from the spiral waveguide. So why symmetry? Symmetry is because of the phase matching condition. This condition is my energy conservation condition, and symmetry of the frequency space. Symmetry of a frequency in a space is because of the phase matching. My 2 kp is ks plus ki enabled by, and this phase matching condition we are getting when we use the waveguide with this dimension 450 nanometer into 220 nanometer. I will explain in the later slide what are the experimental setup of the spiral waveguide. So this spiral waveguide we are using because it has a very good noise reduction. So we want the very good noise reduction to get the single photon and the single photon purity to achieve the theoretical limit of the single photon purity. This is very critical for the high single photon purity, because if we aren't unable to create the signal and idler photon, then how we can create the single photon? The scheme is the heralding. So yeah, so this is the my spiral waveguide. The structure is in a spiral shape, and one spiral waveguide is constitute the cladding is the silicon SiO2, and there is a silicon core. The silicon core has the dimension 450 nanometer into 220 nanometer. So the 450 and 220 nanometer is because of the phase matching condition, and we have a silicon same SiO2 undercladding and the silicon substrate. So my silicon substrate is because of the passive mechanical support. It doesn't, and SiO2 has a refractive index 1.44, and silicon core has a very high refractive index. So there is a no leaking of the photon. So my signal and idler photon generation will go up very high. Like it will generate a huge number of the signal and idler photons. So yeah, this is all the motivation and the losses and all. So key design features of the spiral waveguide is my CMOS compatibility. So if we are able to design this kind of the spiral waveguide, and we are achieving the theoretical single photon purity. So it is commercial. Like we can produce we can do a mass production with this existing semiconductor tech. It's a highlight confinement because of the bend radius, and we are using the spiral, so that's why it is a very highlight. Or we can design it on a chip as well. And this is it is a phase matching condition, so it optimizes the SPWM process. What are the advantage of the quantum? What are the advantage for this quantum application if we are using the spiral waveguide? The advantage is like in spiral waveguide, I am using the silicon. So silicon is my very high non-linear susceptibility compound. It will boost the SFWM efficiency, and it will do a very good noise suppression. And the footprint is because of the dimension. So it 1.3 centimeter waveguide coiled in a 1.3 millimeter into 1.33 meter because of the spiral. So next, after the spiral waveguide, I am getting the signal and idler photon. So I have to distinguish signal and idler photon very 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 separately. So for that I am using the DWDM, which is dense wavelength division multiplexer. So what is DWDM is like my key specification of this channel is the channel spacing is 0.8 nanometer. So it will separate a very good it will separate perfectly passband isolation. The critical function, it will reject
it will reject all the noises. It will only split the omega s and omega I, like signal and idler photon. It will route the photon to the SNSPDs. So SNSPDs is the detector that we are using to detect this signal and idler photon. So what is SNSPDs? By superconducting nanowire single photon. So it has a superconducting. It means that it will work on the cryogenic temperature, which is 2 to 4 Kelvin, and it use something material. It is a nanowire. It's a nano material. It's a nano detector. So that's why so this is the specification of the detector, and the efficiency is 71%. It will detect 71 photon out of 100. So time jitter is 80 picosecond, dark photon is 300 hertz, and critical roles are for why we are using SNPD, especially because do a very good heralding, like idler photon detection. Then we do the signal paired, and for when we are using this SNSPDs, we are getting a very high purity photon having the correlation function at tau is equals to 0.00094, and the coincidence counting is very high, which is 1.51 megahertz coincidence range. It means this is a very good single photon source, which we can use in a quantum communication, quantum key distribution. So yeah, this is the block diagram of all the photon. Like first, the photon is entered in a spiral waveguide, and then the pump, and then the pump divided into the signal and idler. Then we have a phase matching. And then we have a DWDM to divide the omega S and omega I, and then SNSPDs to detect, and then do the coincidence analysis. We have a TSSPC. So yeah, this is the table. You can comparison when we are using different material waveguide, what we are getting, what are the repetition rate, what are the maximum coincidence exponential ratio, what is the minimum GH, what is the maximum rho. So you will know that for the silicon waveguide, we are getting the maximum and the minimum maximum car, that means the perfect brightness, like a optimal brightness, while getting the maximum photon purity, which is a single photon. Next, I'll go to explain some graphs, which is the autocorrelation function of the pump. Like it's a coincidence count versus time. uh, it plots only suggest its plots only give the result, like why we are using ML, what are the effects of ML off and ML on the statistics of the pump photons and the heralded idler photon. So in a first section, when we have a master laser off, the pump photon statistics is 1.539. It uh, it will it is similar to the 1.539 means, and yeah, so 1.539 is like bunched light, and yeah, it is because of the bunching, and you can see at a point 4 nanosecond we have a negative correlation compared to the adjacent peak. When we on the master laser and do the same analysis for a pump, we are getting the coherent source that we are expecting as well. And in the C part, we have a master laser off. We are getting the statistics for unheralded photon is like thermal statistics, because its correlation function at 0 is like greater than 2. And for when we on the ML, it is similar to the 1.23 near to the Poissonian. So yeah, so this is all the analysis, is all the values, like what are in this case, and for the Poissonian, for the stable. So next, Ujjwal will explain the result and conclusion of this paper. So yeah, thank you.
Hello everyone, my name is Ujjwal and I am presenting the result part of the paper. Okay, let's start. So let's have a quick overview what we were aiming that paper. So first, we wanted to develop an experimental setup which can produce heralded single photon sources. What do we mean by heralded? So let's say we have two photons which are entangled, and we are detecting one photon with some detector, and the detection event will make sure that, okay, we have a single photon which was the partner of this photon that we just detected in the other branch. So we use a spontaneous four-way mixing process to generate two entangled photons, and then we use a filter which make a spatial separation in those two beams. So they are called signal photon and idler photon. So we use some filter to make a spatial separation between signal beam and idler beam. Okay, and then we wanted to achieve limits of the brightness and limits of purity. So how bright this single photon source we can make with, let's say, X amount of purity. And then we wanted to optimize all these conditions with using a most suitable nonlinear crystal. So in this case, on chip, we have silicon on insulator as a spiral waveguide, which we are using as a third order nonlinear optical medium that is responsible for spontaneous four-way mixing. Okay. Now, what we get? High brightness and purity. So we were able to get sufficiently high brightness with a good amount of purity and low multi-photon emission. What do we mean by multi-photon emission? That basically we want to reduce the noise. Yeah, so let's move ahead. So experimentally, what we achieved, we got 1.51 megahertz coincidence rate, which is quite good. So what do we mean by coincidence rate? So coincidence rate measurement tells us the simultaneous detection of the signal and idler photon. So coincidence rate means all those entangled pairs which are the result of the SFWM, which we are quite interested in. And then we started with a theory part, and then we tried to match the results. And there were quite good agreement. So also we got heralded correlation function as 0.00094, which is close to 0, which is very close to 0. And as we know that if we have a correlation function at 0 delay close to 0, it means we are moving towards a single photon source. So there's no anti-bunching, or let's say very less anti-bunching, very less bunching, sorry. So there is very less bunching. We are moving towards a single photon source. So for the spontaneous four-way mixing, we use a pump, which is the origin of two photons. And we were able to stabilize that at 2.4 gigahertz. And let's say the rest of the insights we can get from these two plots. Okay, first discuss this single count rate versus pump power. So we have two kind of behavior. First, at the initial point where power is less, we are having a linear fit, while here at the high pump power, we are having a parabolic. So almost is y equals to x square behavior we're getting here. So this red and black, so C39 is for signal photon, while C28 for idler photon. So we have omega S and omega I. So omega S is the frequency of signal photon, while omega I is the frequency of idler photon. Omega S is around 1546, while omega I is around 1554. Okay, so let's discuss the reason behind the fitting. So we have two fitting, linear and square fitting. So for the linear fitting, the reason is the dominance of noise photon, which is basically generating from dark counts and the spontaneous Raman scattering. And this spontaneous Raman scattering is originating from the material that we have chosen, the third order nonlinear optical medium. So that is accidental counts. And in the high region, because we have high pump power, what it does, it increases the probability of production of entangled pairs, which are correlated, which is the aim of the experiment. And now let's move to this coincidence rate versus pump power. So quickly, let's see, at high pump power, it is saturating at 1.5 megahertz, which is quite good. So now let's move to this plot. So this plot shows us the ratio, coincidence to accidental ratio, and coincidence rate. So at high coincidence rate, we have low ratio. And now let's discuss some potential use of, or the overall aim of this paper or of this experiment. So let's say we are able to finally produce a single photon. That's the fact is we are having some noise. The source, the photon is not exactly a single photon, but yes, it can be used up to a certain limit. It can be used in quantum information processing for encoding the information in that photon, which is in some certain state. So summarizing all of that, we have experimental setup on chip in which we are using a spiral waveguide. We are using different elements to perform the experiment, which were grown in home. And then we have some theoretical derivations. And then we did the matching, and the result were in quite a good agreement. So briefly, that was the result that we get as a in the last section of the paper. Okay, that was my part. Thank you.